Today we are going to do section 6.3, which is the Taylor series. The Taylor series is something like this. Okay, first let's look at the function. Let's say that the function has some kind of a expansion equals to some infinite series like this. Now for now, let's not worry about whether it converge, diverge, the interval, nothing. Let's just assume everything works out perfectly and it converges and stuff. And the A is the point where we are expanding this from. Okay, the point is this equation holds for now. So assuming this equation holds and holds perfectly, then we have this, of course, equals to that if you write it out loud. The question is there any way we can figure out what these coefficients are? Because the only thing hard about finding this series is finding out what these coefficients are, right? The x minus a is just x minus a, and to the various powers, 1, 2, 3, etc. So then in the previous sections, we have turned some functions and used their similarity to the geometric series and beat it into a geometric series, and then we were able to calculate various functions and figure out what the expansion is. However, that isn't necessarily always possible. Is there a general way that we can do to any function? Okay, any function such that we figure out what these things are if the series, if everything works out. Now the way to find this actually is quite simple. All we need to do is take the derivative of this stuff if we know what f is. Okay, now if we know the function, then expanding it is simply a matter of taking the derivatives again and again, and I will show you what that means. Now so on page 561, let's say this whole thing. First, let's calculate what C0 is. C0 is simply you plug in x equal to a. Okay, now if you plug in f of a is what is f of a? That would be the second x becomes a, then all these things disappear, right? Then you immediately know what C0 is. C0 is just f of a. Okay, so far so good. But what about that one? Okay, now that we figured out what f of a is, what we're going to do is take the derivative of this thing. Now, if you take the derivative, what is f prime of x? F prime of x, that's the first derivative. That becomes 0, and that becomes c1, okay? And then c1 of just c1, okay? And then plus other stuff like 2c2, x minus a, etc., right? And so on. But the point is, now this becomes the new f in the terms that c1 is kind of like the new c0, because again, then f prime of a will be, if you plug a into x, then it knocks out all the x's, the stuff that has x in it, and then it equals to c1. See, now you see where this is going. So we keep doing that. So then next, let's do the next derivative. So we do the second derivative, f double prime of x, and that equals to, so that disappears if we take the derivative of this function, okay? And then this becomes 2c2, and then plus other stuff. Okay, and it will go on, of course, and we know how to do that. But I will stop here to show you that then f double prime is equal to 2c2, and if you plug a in here, that means f double prime at a, being that, remember, we know what f is, right? We're just trying to expand it. We know what f is, therefore we know what f double prime is, assuming f is differentiable, of course. To the second derivative, well, yeah. Anyway, so assuming f is all perfect and differentiable and everything, then f double prime at a, which we can evaluate, will be equal to the 2c2, which means we can calculate c2 equals to f double prime of a, which we're able to do if you are patient enough to calculate the second derivative of this thing, and divide it by 2. See, then we know what the second coefficient is. And we can continue to do this, and eventually we're going to find out that any of the c coefficient will follow this formula. You just take the derivative enough times, okay, and then everything will come out. eventually what happens is each c of n, okay, by the time you do this, you keep doing calculating the derivative, right? And then eventually c of n will end up being the nth derivative of a, and divided by n factorial. The reason we divide it because each time you c2 divide by 2, and then c3 you have to be divided by 2 and 3, and so on. So eventually you got to n, then it becomes all the dividing has to come out, okay? Because the power gets higher and each time you have to divide. Yeah. So anyways, as a result of that, this is how we can calculate the function's Taylor expansion. That's what this Taylor series is also called, because we're expanding it, right? Well, anyway, so the Taylor series can be calculated by this each Cn can be calculated by a nice fixed formula. This formula, as you can see, is not going to be easy to do. Depends on how fast you can do the derivative. And as the derivative gets higher, each time you have to crank the derivative, and it might get harder and harder and get to be a total pain. But yeah, so the Taylor series is not, a very comfortable thing to do, because you have to take so many derivatives, but it's doable. See, and I mean, with enough patience, you can calculate the Taylor expansion with this formula to however many terms that you need. So this thing is called the Taylor expansion. Now, so let's look at the next page where the definition is officially given. The Taylor series is called, we'll write it all out, which means it's just the summation of f, okay? So you have f of x. The Taylor expansion is the sum from 0 to infinity of the nth derivative. Remember what this thing is. That's the nth derivative at a, where a is where you're expanding. Divided by n factorial, that equals to the coefficient Cn. And then you just multiply by x minus a to the power n, where n goes from 0, 1, 2, and forever. For as long as you have the patience to calculate the nth derivative, which is not going to be an easy matter, but it's doable. See, and that's the beauty of the Taylor series. So at least theoretically, is able to now we don't have to try to force something into the geometric series, which may or may not work, and may or may not be possible or something. And now we don't care. Okay, as long as the function is differentiable to the nth power, and we know how to differentiate it, then the Taylor series will pop right out conveniently, because we have a complete definition of how it's done. I mean, complete method of how it's done. Now, the next thing we need to look at, I should mention that when a equal to 0, the book calls the Taylor series as 0 Maclaurin series. So if you see in the homework they talk about Maclaurin series, it just means the Taylor series at 0. Next, uniqueness. Now, if there is a Taylor series, then it has to be unique. Yeah, all right. Anyway, that's because power series is unique in general, and Taylor series is just a type of power series. So then it follows to be unique as well. That just means you won't be able to come up with two completely different Taylor expansion. Okay, that is, if you find a Taylor expansion, that's the one. Okay, there's no other. Two people are not going to find two different ones. If you do find two different ones, something is either that they just look different but actually the same because of some calculation, or you mess up. That's all I can say, right? Okay, so next we have now that we have the infinite series, which is the Taylor series, the finite one, where we have the nth Taylor polynomial, that just means we don't add it to infinity, we only add it to the nth term, which is what we normally do, because who's going to add stuff to infinity? Well, sometimes it's possible, right? But most of the time we just add it to the nth term, and then we're too tired and quit. So that nth Taylor series polynomial is just when you stop at n, and that would be called the nth Taylor polynomial because it stopped. And these are all polynomials because, as you notice, that the expansion is x squared, and so on. It stopped. If it stops at one point, it has a higher power, but it's still just a polynomial. All right. And then, and of course, if a is 0, the book will call it the Maclaurin polynomial. And so if you see the word Maclaurin, remember that it just means the Taylor series at 0 when you're doing your homework. Now, so having said that, let's look at example 6.11. Now, what is that? We are going to do natural log of x to find the Taylor polynomials, okay, for natural log of x. Now, to do that, you just follow the recipe, okay? You're supposed to do the function and then calculate the derivative up to, they want you to do all the way up to p3. So calculate derivative all the way up to 3 and then write the stuff out. So that's very straightforward, although tedious. So please do that as part of your homework. Example 6.11. So next, let's look at example 6.12. The same thing. You need to find the Taylor polynomial up to P3 for S0. S0 is slightly easier. You don't have to write down the subtraction, okay? Just X. And that. Now, if that's the case, now you have to, example 6.12 is important because those are the 8. You have to do ABC, which is for e of x, sine of x, and cosine of x. Now, now they are important because they are the 3, probably the easiest Taylor polynomials you can possibly develop. Why? Because you'll be taking a bunch of derivatives, right? And you just have to keep doing the 3rd, 4th, 5th derivative, which is which can easily become a huge headache, except that when you do e of x, the derivative of e is e. So that it doesn't change at all, which is very convenient. And the derivative of sine is cosine, which then turn back into sine again. So it's slightly less convenient, but still very nice. And then the cosine is the same thing. So then, so please find the Taylor polynomials for e, sine, and cosine in example 6.12 up to P3, okay? That's all you have to do, I guess. So yeah, please do that because this example will later be used in various homework and even the text for future examples will refer to this. So it would be good for you to, in fact, memorize the Taylor expansion for e to the power x, because it is used a lot and it's very short too. So please do example 6.12. Next, let's go to page 568 where we'll talk about Taylor's theorem. Now, Taylor's theorem states that, let's say we have what is this? The polynomial, the partial sum of the Taylor series, where we added stuff all the way up to n of the Taylor series, and then we stop there. Okay, and f of x is the original function, and this is the expansion that stops at n. That's called Pn of x. Now, we will define Rn of x as the remainder. That is what's left. Okay, the remainder then we'll define it as the difference between the original function and Pn of x, which is fine, right? That would be what's left. You subtract the difference, whatever the difference might be. The Taylor's theorem says the difference will be this. Okay, here's the difference, and here's what we are going to prove: is that the Rn of x we will prove that Rn of x is something like this: is equal to fn plus 1 of some point c, where c is between x and a, and then divided by n factorial. N plus 1, I mean, n plus 1 factorial times x minus a to the power n plus 1. So we're going to prove this step right here. Okay, now how would we prove that? Now we'll go to the next page, and there is a very neat proof, although lengthy, but not necessarily very convoluted. So what we're going to do is pull a neat trick. Okay, to prove this fact, we're going to define a certain function that's within the interval of our conversation here. Well, for this theorem to make sense, of course, f has to be differentiable all the way up to n plus 1. Let's see, I should probably read what it has to be differentiable over. Yeah, the condition is the f has to be differentiable n plus 1 times, and on an interval, and then, yeah, that's about it. Because right now we're only talking about the finite, the Pn of x, which is the finite number of terms. Okay, we're not talking about the infinite series. So we're not worried about convergence, so to speak. We're just trying to calculate, if we were to expand it into a finite number of terms, what is the remainder going to be? So that's all we're doing right now. So to do that, we are going to pull a neat trick that is called, all right, so for the interval that we're concerned with, we will define a function g, okay? And then we're going to fix the x for now. That is, x is a variable in the interval that we're thinking of, but we're not going to let it move for the moment. We'll focus on one x at a time. And we're going to define a different function called g of t. And this is on the following page of the proof, where g of t is equal to, I'll write this thing down. Okay, I wrote out g of t, and it's a big long thing and has both t and x and a in there. Now do not like, does it have a? Yeah, I think so, right? A is at the very end. The thing is, you see, wow, why does it have so many variables? Now remember, x and a are both fixed. That is, they're constants in g of t. We are defining g of t for one of the x's. And so x is held constant in this situation. And so x does not change, okay? So it acts like a constant in this function. The only thing that's changing in here is the t, because it's a function of t. So x and a are constants. And we specifically designed g of t this way. Now, why are we doing this? Well, as you can see, g of t very much resemble this thing, right? And for a reason. We're going to trap it and make it work for us. This is called we don't care what it's called, just that we're going to use g of t and use it to prove that our n of x happens to equal to something like this. And that's why this thing, see, this thing looks very much like it. And so this whole thing is designed to help us prove Taylor's theorem. Now that you have accepted g of t, well, it's just something we made up. Okay, so we made up this very specific function. Remember, x and a are constants in this function. Okay, the only variable is t. So having done that, the next thing we're going to talk about is something called the Rolle's theorem from Calculus 1. Now, if you don't remember what Rolle's theorem is, Rolle's theorem basically says if you have g of some one point, okay, in this case, let's say a, and if you somehow can prove it equal to 0, and then g of another point, let's say x, it also equal to 0 if this is true, okay? Now, by Rolle's theorem, if these two things are true, then g prime of some point called c will be 0. G prime means the derivative. The derivative of some point between a and x, where c is between a and x. Let's say something like that. C is bigger than a and x. Assuming, or the other direction of the inequality. The point is c is somewhere between a and x, such that the derivative equals to 0. The Rolle's theorem comes from Calculus 1. Please look it up if you don't remember a word about it. It's just a type of the mean value theorem. And anyway, so now that we know this, we need to prove that g of a and g of x is 0. Okay, if it's 0, then this fact will stand. But is it 0? So then we now calculate what is g of a. Okay, if you plug a in here, where that is set t equals to a in this formula. If t equals to a, then everything becomes, let me see. Now, g of a equals the first term is f of x. We'll write that down. Equal to f of x. Then from the second term, if f of a minus x minus a, and the f prime, the t becomes a in all these things, right? Then what is that? All the way up here. That's exactly this thing right here with Pn of x. See, Pn of x is term by term identical from this part all the way to here with t equal to a. So then we can write it down. It's just Pn of x. Okay, because Pn of x equals from here all the way to here. And then next, and the last point, we minus Rn of x. And what's that? Remember, t is now a, right? If t is a, then this cancels out, right? T is a. So then that becomes 1. So we only have this thing left. So far, so good. And what is f of x minus Pn of x? Well, by definition of Rn of x, this is Rn of x. So this value, g of a, therefore, equal to 0. So we got this thing to be equal to 0. So far, so good. Next, we'll look at g of x equal to, next we need to calculate what g of x is. Now, g of x, we do the same thing. G of x, if we plug t equal to x now, okay? So t equal to x, and then this f of x minus f of x, and all the other things, you know, t is now x. So it becomes 0, 0, 0, everything's 0, including this one. So it's all 0. So g of x, therefore, equal to 0. Then we have proved this by Rolle's theorem. There exists a c such that g prime of c equal to 0. Okay, so g prime of c equal to 0. There exists a c. We'll write backwards. E means there exists c prime, g prime of c equal to 0 for c between somewhere c is between x and a. Yeah. Anyway, so that is true by the Rolle's theorem. So we have come pretty good. And next, okay, now we have figured out that there exists a c such that g prime c equal to 0, where c is between x and a somehow. Then we need to calculate what is g prime of t so that we can figure out what g prime of c is. Now that means we know what the g is defined, so we just need to do the derivative of this entire thing. Goes up there all the way across. Yeah, so please do that as part of your homework. That's a big long pile of algebra, right? But it's still only taking derivatives, which is done in Calculus 1. And you're taking the derivative of polynomials. So it's strictly speaking an easy job, but very, very tedious. However, when you're done, you will realize that the g prime of t end up being 2 terms. This thing right here, which is long, but remember, the original one goes on, right? It has a whole bunch of stuff added up. So how did it end up being just 2 terms? The reason is because there's a telescopic effect in where stuff got subtracted out. Things keep subtracting by the next one. Now, as you do it, you will find out what I mean. So please do the derivative. Calculate the derivative of g prime until you come up with come up with this whole thing as part of your homework. Okay, you have to make it come out to look like this. Now, once you get it to come to find out, g prime is just, that is, the derivative of g is only 2 terms, even though g has a ton more terms than that, because it's subtracted out in a telescopic way. And therefore, we know then that g prime of c equals to these things added together, which still looks pretty complicated, but it equals to 0. Once we know that, then you notice these terms, okay? If this whole thing equals to 0, then you can get rid of this, cancel out this x minus c to the power n, and then move everything to the other side of the equation except Rn, and you end up with this nice, neat formula. So as you can see, the g of t is a beautifully designed function that somehow ended up with us figuring out exactly what the remainder is in the Taylor theorem. All right, so that is the end of the proof of the Taylor theorem. I should, of course, mention that because Rn of x is defined this way, if we can find a maximum value for this thing right here, and because c is between something, right? I mean, between x and a. So then if we can find out what's the maximum this can be, then we can find out what the limit, I mean a bound for the remainder. Okay, so then as your book puts it, then if we can figure out what does the limit of, what is the bound for the function, the nth derivative, if it's bounded by something, then the entire remainder is bounded by the same deal. So that will enable us to put an estimate on the remainder, which you will be doing in your homework by using this formula. So that is a very neat proof of the Taylor series. See? And as you can, yeah, this is like a stroke of genius, right? You just arrange the whole thing out and everything just fall into place. And all you have to do is quote the Rolle's theorem from Calculus 1. And of course, you got to take the derivative, which is slightly tedious, but not bad, about what, 3 lines or something? And you just have to write a bunch of stuff within those 3 lines. So please make sure you do that as part of your homework. That is calculating the derivative of g of t. Now that we are done proving the Taylor series, which has such a neat proof, and we have to do the homework. Now the homework, the examples. The examples, however, are just a matter of, is not near as ingenious. Now we have to actually do it, okay? We know how Taylor series works. Now you have to get your hands dirty and start calculating derivatives and plug it in and do all this, divide by the factorial and do all that stuff. And then, and also, of course, estimate what this nth thing is and how big can it be, and then calculate the remainder. All follow the recipe and do your grunt work. So that is, which is example 6.13, and then 6.14 and 6.15. So please do all 3 as part of your homework. They are probably quite time consuming, but as a whole, they are not, I don't think there's any trick to it or anything like that. So they're totally doable, but you better plan for some time and patience to, do all this stuff. Anyway, so next we should mention the convergence of Taylor series. Now, how do we know this function, the Taylor series, will actually converge into the original function? It better converge, otherwise what are we talking about, right? The Taylor series converges if the remainder converges. That is, we just, because the remainder is the difference. So then if the remainder goes to 0, then as n goes to infinity, then the Taylor series obviously converges. So then that is, what am I talking about? Page 574, theorem 6.8. So the convergence is converges on the interval if and only if the limit of Rn of x as n approach infinity goes to 0. Now, this is one of the first time that I see the term if and only if used in calculus. The if and only if means that both conditions always come together. That is, if A, then B, and if B, then A. So it is not possible for one to show up without the other. Okay, that's what if and only with if means. It basically, whenever you see the term if and only if, it means it's true A implies B, but at the same time you also have to think B also implies A. So it's like 2 sentences combined in one. All right, and then example 6.16, which we are going to do more work for the e and the sine of x, where you have to show that this thing converges by proving that the remainder approaches 0, which is similar to what we've done so far in the previous sections, proving series converge by the ratio test or something, and that's what you need to do. So that's example 6.16. Please do that as part of your homework. And that marks the end of the section. So in the next video, I will tell you what the homework is. I am not done with it yet.